Good afternoon, and thanks for joining our webinar. We're going to wait just a minute or so to get started to give everyone that hasn't arrived the chance to jump online here. Okay, let's go ahead and get started. Hello, everyone, and welcome. My name is Carolyn Kushwa, and I am a Marketing and Communications Specialist at Testo North America. We have a great session for you today on understanding superheat, subcooling, and saturation. To kick things off, let's go through a few logistical matters. Our session today will run about an hour. We have all attendees muted, but we encourage you to submit questions in the questions panel to be answered at the end. We are recording the session today, and we will send the recorded version of the webinar to you afterward via email. Now I'll go through a brief introduction to Testo and our products and services. For over 60 years, Testo has stood for innovative measuring solutions. Testo helps over 650,000 customers worldwide save time and resources, protect the environment, ensure quality, meet regulatory expectations, and increase the value of their goods and services. Testo is a major supplier of monitoring instruments for markets as diverse as chemical, food service and production, pharmaceutical and biotechnology, as well as commercial and residential HVAC suppliers. Our speaker today is John Feigen. John is the Southeast Regional Sales Manager for Testo North America. He has over 20 years of work experience with Testo and another 18 years with other HVAC instrument manufacturers. With over 38 years of experience in HVAC instrumentation and as the Southeast Regional Sales Manager for Testo, John also trains and educates end users on HVAC products and applications in the markets of HVAC, industrial, weatherization, safety, and gas utility. John is a certified NATE instructor and conducts technical NATE training classes for Testo on primarily two NATE certified classes, Superheat, Subcooling, and Saturation for AC contractors, and the importance of combustion testing for heating contractors. John is a graduate of Penn State University with a combined major in marketing and environmental science. And so with that, I'm going to go ahead and turn things over to John to dive in.
Thank you, Carolyn, and welcome everyone to the presentation. I welcome everyone, and I want to thank everyone for attending. This is a NATE certified program, so that means that this is more of a technical presentation rather than a product presentation on our instruments. And what we're going to cover today mainly is the refrigeration fundamentals. Hold on for a second here until I get the slide up. Hey, Jolie, did you pass this over to me? Control the presentation.
Well,
oh, okay, they were part of it. Okay, sorry about that. Now I get control. Thank you. But the first 6 parts of this presentation, the 6 bullets here, we're going to go over the presentation. It's really a basic air conditioning presentation, looking at the fundamentals, heat transfer laws, looking at refrigeration cycle, a lot of things that this may be a review for a lot of you on board, but I think it will be a good review. And then a last couple bullets there, we're going to go through the technology that's used today in in doing our air conditioning and refrigeration service work. Julie gave, or I'm sorry, Carolyn gave a great presentation on Testo. I just want to mention a little bit about Testo on the HVAC side. We're the largest group at Testo. We have a lot of different divisions, product groups, but the HVAC group is a very important part of the total Testo entity. As you can see here, we have a long history, as Carolyn mentioned, but also I like to just bring up a little bit about the 17025 standard. We have a calibration lab in New Jersey. That's our headquarters. It's in Sparta, New Jersey, in addition to Westchester. But Sparta, we're certified IOS 17025, and what really that means is we have an international standard for testing and calibrating instruments. So regardless of what you're using on Testo, whether it's an airflow hood, a combustion analyzer, a thermal imager, or even the digital gauges, which we're covering today, they're all tested through procedures and protocols, and it is all about the accuracy of instruments today. So let's get into a little bit, enough about Testo. We'll get into a little bit about the presentation and the technical side of this. But the reason why we're testing, and we HVAC, we're all testing, hopefully we're familiar with Testo in some areas of instrumentation, but we're testing because we want to provide customer value. That means that we want the OEMs, the Carriers, the Lennox, the Goodman, the Rheem, the Howell, the Trane. We want to meet their OEM recommendations on operating at peak performance. We want to make sure we do that to provide customer value. We're all professionals out there, and yes, we are all the experts. We are considered the experts in AC and refrigeration equipment. So we have to know a little bit about the science and the physics behind how a system operates. There is some safety issues. We have to maintain certain safety issues, again, to OEM recommendations or to local regulations within a certain geographic territory. And last but not least is profitability. We're all here to make money. We want to make money, but we want to make money, but we want to make sure that we're doing a good job. We want to reduce the callbacks. We want to make sure we get the job done right the first time. And when we do that, that's where we can see our increase in profitability. As we get into the laws of refrigeration and heat transfer, I'm just going to go through a few of these, and I think a lot of these that you heard of before are very common to AC equipment. And again, there is some science behind HVAC, and we need to know some generalities or some general things on the physics of an air conditioning refrigeration system. But let's take a look at heat. Always moves from a higher temperature to a lower temperature. We all know that it's always a movement of heat from hot to cold, or from more heat to less heat. Absolute zero, I kind of ask this question a lot. What is absolute zero? Absolute zero is at minus 460 degrees Fahrenheit. I can't recall what it is in degrees Celsius right now for the Canadians on board, but when we have absolute zero temperature, that means that there's no molecular movement. That means the molecules are not bouncing back and forth, and we're at what we consider absolute zero. As soon as those molecules start to move faster and faster and faster in matter, it's creating some infrared energy and it's creating heat. So minus 460 is absolute zero, no what they call molecular movement. But as we get into minus 100, minus 5, 32 degrees Fahrenheit, 0 degrees Celsius, we have molecular movement. And the movement of those molecules are creating heat. And that heat is measured in the way of temperature. Gas laws, P and T, pressure and temperature, are directly proportional to each other. As pressure increases, so does the temperature, and vice versa. This is the basic law in air conditioning, what I consider one of the most important, because we're increasing pressure at the compressor, we're decreasing pressure of the fluid or the refrigerant at the metering device. And we'll go through that in a little bit more detail. Fluids absorb heat, or refrigerant absorbs heat while changing from a liquid to a vapor state. Happens in the evaporator, and fluids give up heat while changing from a vapor to a liquid in our condensing unit. So let's take a look at this chart here. We know that we have different states of matter. We have a liquid, we have a solid, liquid, and we have a vapor. Now, if we look at this chart below, if you look at the horizontal axis, which is this axis on the bottom here, that's the heat that we apply to something. We're adding more and more heat in BTUs. Here is the temperature from 0 degrees Fahrenheit to 300 degrees Fahrenheit. And what this illustrates here is this illustrates how water changes state as we add heat to water. And I use water as an example because water we can all visualize. We know that 212 degrees at sea level, water's going to boil at sea level. Or it's 100 degrees Celsius, it's going to boil at sea level. Same thing with 32 degrees. We know that at 32 degrees, water freezes. At 0 degrees Celsius, water freezes. I like to use water as an illustration here because if you look at R22 and R410A, R22 boils at minus 441 degrees Fahrenheit, whereas 410A boils at minus 61 degrees Fahrenheit. So by looking at water, we can visualize easily that as we add heat to water, and that's called sensible heat because we can measure it. Something that we can measure is called sensible heat. As the temperature rises and we're adding more and more heat, it reaches a point where at 212 degrees and at PSI at sea level, which is 14.7 PSI, you're gonna see what we call saturation taking place. That means that the water, the liquid, and the vapor are changing state. In this case, liquid is changing from a vapor. And when we have that taking place, which happens in the coils, we have no temperature increase. That increase, it stays constant until we reach a point where we create steam. All the water, all the liquid has turned to a vapor, and now we're looking at steam. And the steam now increases to 213, 215, and so forth. This happens in reverse. As we take away heat, we have all vapor. The vapor then comes to a point where it starts to condense to water. So we have a point where we have a mix of water and steam together, or saturation, and we have a steady 212 degrees Fahrenheit. We reach a point where we have all liquid, then we have a decrease in temperature as we decrease the heat. So in this case, we're using water. In air conditioning and refrigeration systems, obviously we're using refrigerant that boils at very, very low temperatures. And as I indicated before, R22 boils at minus 41 degrees Fahrenheit. The top of this here is considered superheat. Anything above the saturation point is considered superheat. Anything below the saturation point or the boiling point is considered subcooling. So in air conditioning, we have components. We have the compressor, condenser, metering device, evaporator, refrigerant itself. Each component here contributes to changing the state of the refrigerant. Let's go through this for example. A compressor is considered a pressure increaser. It's increasing the pressure of the vapor and creating creating a high pressure, taking it from a low pressure to a high pressure. The condensing unit, is the part of the unit that surrenders the heat to the outside. In this case, we have more heat in the refrigerant because it's coming directly from the compressor. We have less air, ambient air or outside air, and there's going to be a transfer of heat from the refrigerant to the outside area. We also have a metering device, and these metering devices can be fixed or they can be TXV. A lot of them are TXV today. And as we look at a compressor, this increasing pressure, this metering device is a pressure dropper. It's going to reduce the pressure before it gets to the coil. Less heat in the refrigerant. So in this case, we got hot air, distribution air going over the coil, which is a little colder or less heat, and we have a transfer of heat from the distribution air to the refrigerant. In this case, the opposite of a condensing unit. So the refrigerant itself is a heat mover. It's moving the heat from an area where we don't want it, which is inside a home or a building, to where it's more acceptable, which would be outside at the condensing unit. So if you look at all these components together, let's take just a look. You see the compressor somewhat in the center, and we have red arrows indicating a refrigerant gas state. We have blue arrows that indicate a liquid state. And let's just remember hot to cold, that heat transfer law. Like, you ever hear of follow the money? Well, this here, you want to follow the heat. So let's start at the compressor. The refrigerant vapor is compressed in the compressor and now moves to the condenser. The refrigerant is at a high temperature, high pressure vapor. If there is more heat in the refrigerant and less heat in the outside air going through the condensing unit, the condenser coils are transferring the heat from the refrigerant to the outside air. As the refrigerant rejects the heat in the condenser, the refrigerant condenses and becomes a liquid. So you have a vapor to a liquid change in the condenser. At the condenser outlet, the refrigerant is now at a high pressure liquid. The high pressure liquid refrigerant travels to the metering device. In this case, we have a TXV located right here. The metering device is a pressure reducer and therefore drops the temperature of the refrigerant and the pressure as it travels to the evaporator. Now the refrigerant is cold, or another term would be have less heat as it enters into the evaporator. Once we get into the evaporator, now there is more heat in the room air as it passes over the evaporator coil, and the heat is being transferred to the refrigerant from the distribution air or the air to the refrigerant, and as a result, the refrigerant is going to boil and it's going to change from a liquid to a vapor. At the outlet of the evaporator, the refrigerant is now at a low temperature, low pressure vapor as it travels to the inlet of the compressor. And this cycle continues and continues and continues. It's a pretty remarkable system in my opinion, and not many people understand how a refrigeration or AC system works, especially the customers, whether they're residential, maybe some commercial, but not many people can understand the physics behind how an AC works. And it's up to us to understand the concepts behind this, because we're taking measurements. We're looking at, we got to take measurements. We got to know what the pressures and the temperatures, the relationships of those pressures and temperatures are across the entire system. One thing too is we have a blower here. It creates airflow across the coil. the evaporator coil, and we have a fan over here that creates airflow over the condensing coil. And it is important today that we measure airflow. It's one of the first things we should be doing on a system. And airflow is it's critical for system performance. The nominal 400 CFM per ton for AC units, roughly around 450 CFM cubic feet per minute ton for heat pumps. So this is important. It's we have a whole seminar uh, just devoted on airflow because it can get complicated, just like anything else in HVAC. But there are instruments out there that measure airflow. We can do it a lot of different methods. We can use the temperature rise method. We can look at static pressure through a differential manometer. We got a lot of different vane anemometers. We got duct thermal anemometers that go internal into the hard ducts to measure airflow, and we can convert that to CFM. And we also have flow hoods, which are used a lot by contractors, mechanical contractors for test and balance. Not only is airflow to improve equipment performance, but lately, over the last 2 years, airflow is being measured quite more frequently because of indoor air quality issues, primarily because of this COVID-19 issue that we have had over the last few years. By improving the airflow, we can improve the indoor air quality, and certainly that has taken that a big step forward, measuring airflow in commercial buildings as well as residential homes and buildings as well. So enough with the airflow side. Let's get back to the AC side. Before we get into the superheat and subcooling, I just want to go over a few definitions. One definition that we use is dry bulb in HVAC. Dry bulb is just ambient air temperature. We use measurements like NTC probes and K thermocouples to measure dry bulb. In HVAC, we have a lot of terms in HVAC that mean kind of the same thing, but you may see dry bulb. What dry bulb is it's ambient air temperature. Relative humidity is the amount of water vapor present in air. We measure relative humidity probably almost in every job that we go to. It's not only for comfort, customer comfort, it's also for looking at targeted superheat, looking at capacity tests, low capacity tests. Maybe it's comparison, relative humidity comparisons in a building. So instruments today are primarily digital. When they're digital, they can measure relative humidity and they can measure the dry bulb or the ambient temperature, and we can calculate the wet bulb of the measurements. And basically, what wet bulb is it's the amount of moisture um, um, uh, versus the ambient in the air. And we used to use a sling psychrometer where we used a dry bulb and a wet bulb. And as we spun the sling psychrometer, we had airflow going over that wet bulb, which was moist with water, and we could determine the evaporation point of water, how it affects the temperature, and that was considered the wet bulb reading. And from the wet bulb reading and the dry bulb reading, we could get the relative humidity reading. Today, we're using digital gauges. Hopefully, everyone's using a digital instrument for relative humidity. These things are extremely accurate. They're not that much money, and you can do a lot of different things with them, including comfort zones and air comfort zone testing. Just to give you an idea what the accuracy, wet bulb reading is required. A very accurate wet bulb reading is required, and these relative humidity instruments provide that. They also they don't have displays on, or you can get it with a display, but most of it's going to your smart devices, either a cell phone or a tablet of some sort to communicate the information. Now, we get back into the pressure side of things and getting inside the air conditioning system itself. As I indicated on that previous slide, as we add heat to the refrigerant, we're changing the refrigerant from a liquid to a vapor. And as we remove heat, we're going from a vapor to a liquid, or it's condensing. So if you look at this illustration here, we are dealing with saturation, a term called saturation in sealed vessels, which is an air conditioning refrigeration system. We consider the term evaporation when we're boiling water because the liquid is escaping out of the device. Whereas in an air conditioning system, we shouldn't have anything escaping. If we do, we have obviously a refrigeration leak, and that needs to be corrected. But if you see by saturation, we're adding heat, and the molecules are changing from a liquid to a vapor. And then when we remove the heat or the pressure, when I say add heat, we're increasing pressure because we increase temperature. When I say remove heat, we're decreasing pressure. We did decreasing temperature. There, as we indicated before, that's a heat transfer law. Pressure increases, temperature increases, and that's what we're doing primarily in the systems. So what is superheat? Well, we talked about it a little bit already. Superheat is the temperature of the vapor above the saturation temperature. Subcooling is the temperature of the liquid below the saturation temperature. And the saturation point, or the point at which we see a change of state, is where the refrigerant can no longer absorb or lose heat without changing that state. If we go back to that graph that we showed earlier, and an easier way to remember this is that superheat is everything above the saturation, and there is no liquid present up here in the superheat area. Subcooling is that there's no vapor present, it's all liquid. That would be in this area here. And then saturation is where you have both liquid and vapor present because it's going from one state to another as we increase pressure or as we decrease pressure. So why are we talking about superheat and subcooling so much today? Well, compressors are only designed to pump vapor, and our superheat ensures that no liquid enters the compressor. Our metering devices must have a solid column of liquid to operate correctly, and subcooling ensures that a solid column of liquid enters the metering device. Now, as we indicated, we're doing a refrigeration charge. We're using a superheat. We're using subcooling. A lot of times on fixed orifices, we may be using superheat, verifying evaporation performance. Subcooling, TXV, assures adequate refrigerant for proper metering. So we have two different types of orifices that we're looking at today. To check the superheat and subcooling, when we're checking superheat and subcooling, why do we check it? Well, we need to check it when the system is not cooling properly, when the compressor, or any time we break into the system, or if the compressor is replaced, TXV is replaced, the refrigerant charge, the refrigerant changed or it was added to the system. Everything the superheat and subcooling needs to be checked in an AC system. If we go back to the analog method, we're all familiar with the analog method where we use pressure temperature charts, conversion charts. We use a pressure gauge. We use an accurate thermometer. We're using the three measurements and doing the math to calculate the refrigerant, the superheat. In this example, we have 410A. Maybe let's say we have a low pressure of 140 degrees PSIG, and that's PSIG is a gauge pressure. We start at 0 on our gauge. So if we have at 410A, and we have 140 PSIG on our vapor side, or low pressure side, then we have to use a PT chart or a corresponding gauge temperature to get the saturation temperature of 49 degrees. We still have to measure our line temperature. We get 63 degrees. We just do a little bit of math and we get the superheat calculation. Today, and probably many of you on this conference or the seminar have maybe some digital gauges or smart probes. This is kind of the wave of the future, and I'll go through that a little bit later and on why. But these are a little bit quicker, a lot more accurate, certainly a lot more accurate, and you're getting your readings simultaneously, both the superheat and the subcooling simultaneously. So what you're looking at here is you're connecting the digital pressure gauge to the low suction side. So you'd have the blue hose connected to the low side. You have a pressure temperature sensor, a wireless probe connected to the low side suction line, and the instrument's going to automatically calculate for you the saturation temperature and the superheat calculation. Very quick, very fast, very accurate. Again, another case where you're looking at the low side suction line temperature using a thermometer, a wireless probe, and again, getting the calculated superheat automatically. Here's where we would be testing. Here's the service ports for the superheat and the subcooling, or I'm sorry, superheat temperature, superheat pressure, and then taking those readings automatically and getting the readings either through an analog gauge or through a digital gauge. Typically with superheat using TXVs, typically the nominal or the normal range of a TXV for superheat is 8 to 12 degrees Fahrenheit. We used to calculate this way back. Maybe some of you on board can recognize the formula for getting the targeted superheat. Maybe you used charts before, looking at the wet bulb temperature and the return air wet bulb temperature and the outdoor temperature. Today, again, we're using digital gauges that do this on digital, excuse me, instruments that measure relative humidity, temperature, and wet bulb readings, and they can be located on your system, or you can store the readings into your app. But let's say you got a return air wet bulb reading inside the home. You've got one that's outside near your condensing unit to get your outdoor dry bulb, and the instrument automatically would calculate your targeted superheat. This is when you're using your fixed system metering devices, your capillary and your piston. You'd need to figure out the targeted superheat. And with today's instruments, by using two of the digital gauges, which actually are Bluetooth right into the gauge, and I apologize to the United States here, but this is in degrees Celsius instead of Fahrenheit, but it would read degrees Fahrenheit in the States and degrees Celsius in Canada. But these would input the data to get your targeted superheat, and your instrument would read your pressures, your temperature, your line temperatures, your targeted superheat, and your actual superheat automatically. So it's giving you a quicker, faster reading, a more accurate reading, and also a reading that is real-time measurement. Subcooling on the other side is also an important measurement. The metering device needs to operate and have a solid column of liquid entering the orifice. So in a way, we do the same thing. We use some PT charts. We may be using PT charts. They have a gauge, a high pressure gauge, measure the high pressure side. And again, if we use example 410A, here we have 432 degrees PSIG, or I'm sorry, 432 PSIG, which we measure. We convert that to 122 degrees Fahrenheit from the saturation temperature chart. We still got to measure our liquid line, and we do the calculation to get the 12 degrees Fahrenheit subcooling. Again, digital instruments, you'll see two sides of a digital instrument here. One side is the low side, one side is the high side. You'll see two temperature probes here. One is for low, one is for high. Two pressure probes here. One is for low, one is for high. And then you have a kit that shows your relative humidity, sensors. Same thing. You're looking at high side liquid pressure, getting the readings automatically, seeing the 432 psi, which is converted to 122 degrees Fahrenheit saturation temperature. The probe that is on the high side is measuring the 110 degree Fahrenheit. So we're automatically getting and calculating the subcooling of 12 degrees Fahrenheit. Quicker, faster, and more accurate. Again, looking at where we're taking the test on the high side of an air conditioning system. And subcooling is a design number. Therefore, it's found in the installation manual or on the nameplate. So it is a requirement. It is supplied by the OEM, the equipment manufacturer. So we got a lot of measurements we can do. We can do all these measurements here, and you can see by using a digital gauge that it's a lot quicker, a lot faster, and a lot more accurate because we're looking at everything simultaneously. We're looking at the superheat, the subcooling side, both together if we want to. We're looking at low side, high side pressures. We're looking at low side, high side temperature measurement, and we're doing all the calculations. If your superheat is too high, then not enough refrigerant is being fed, resulting in a poor refrigeration or excess energy. Superheat is too low. It's being fed, too much refrigerant is being fed into the system, resulting in liquid getting back into the compressor and causing some issues. Subcooling is too high. The refrigerant was cooled more than normal. Subcooling is too low. The refrigerant did not lose the normal amount of heat traveling through the condensing unit. So the technology behind what we're using today has certainly changed. We're no longer using as much analog gauges or sling psychrometers. And there's a lot of things to look at. And one of the biggest things to look at is the sensor technologies that are available to us today. One of the biggest measurements, or the most important measurements we could do, is for temperature. And we have two ways of measuring temperature. We have thermocouples, which most of you are familiar with. That would be this one right here with the it's based on voltage measurement. And then we have what we call resistance measurement, which is an NTC probe, which are these two probes right here. The NTC probe, as temperature goes up, resistance goes down. It's a little bit easier for us to measure. Type K thermocouple has two dissimilar metals joined together, and we're measuring the voltage change. As voltage changes because of temperature, we get the temperature change, which we can output on an analyzer. And if you look at the NTC versus TC thermocouple, you'll see that there's a wide temperature difference. NTC is only good up to 300 degrees Fahrenheit or 150 degrees Celsius. NTC is a very accurate measurement to use on refrigeration and air conditioning systems. NTC has a much lower, wider range, up to almost 2,500 degrees Fahrenheit. And this is used, we use K thermocouples a lot in our heating instruments, our combustion analyzers. But typically the preference today is for low temperature applications, NTC temperature technology is really the way to go. Just a graph showing that a thermocouple can drift over time because of the two dissimilar metals. There is some offset where when there's any type of offset, we got to calibrate. We got to calibrate a thermocouple periodically, once a year, if preferable. It's tough to calibrate a thermocouple. There's no real calibration method other than ice bath, which is kind of unreliable, or maybe boiling water, depending on what elevation you're at. But You do have to calibrate thermocouples. Nice about NTC probes is they got very good range for refrigeration and air conditioning systems. They are much more accurate than thermocouples. They're more stable, and they're very quick on response time. The biggest thing here is that NTC probes never need to be calibrated. They are calibrated once at our factory, and they will last the life of the instrument. And most of you may have noticed that who are using Testo, that you may have some old probes, and when you turn your instrument on, after using it for 2 or 3 or 4 years, you'll get in ambient air, you'll get the temperature will read almost plus or minus zero point 0.1, a tenth of a degree difference when the two temperature probes are next to each other in ambient air. So what we have a lot of questions today. We have a lot of concerns. We have issues taking place. It's all about providing good customer service, good support, uh, lowering the the replacement calls or the field calls, the warranty calls, the callbacks. So we're trying to maximize our time, our profit by and minimize the time that we spend in testing. And there's been a lot of events taking place, especially after a very long, hard, hot air conditioning season that we had this previous season. And quite honestly, there's areas in my area. I'm a regional manager for Testo in North Carolina, and we're still has some hot days in the upper 80s, and certainly Florida has some very hot days as well. But there's a lot of answers to your questions. I mean, you may have a lot of questions on this new technology. Um, many, there's questions that we could ask ourselves. And if we look at every question on here, what it comes down to is there's some inconsistency on the way and how we are testing for superheat and subcooling. There's different ways of doing it, different methods of doing it, different instruments, different gauges. Um, and what if we get back just in the accuracy of analog gauges, there is less accuracy on analog gauges. I mean, you're talking about a gauge that was developed in the late 1800s. It's just a board and tube, which as we add pressure, it expands and contracts as we reduce the pressure, and that moves a needle on a gauge. And we've come a long way since that. These were good back in the 60s and 70s and 80s, where we had less forgiving refrigerants, but with the higher SEER ratings, higher capacity equipment, the change in refrigerants, I think everyone here knows that we need instruments that provide much better accuracy, calibration errors, repeatability, and certainly, we're not doing the beer can cold anymore, other than if you're drinking one. So the questions you have, again, I think it comes down to the newer technology, and this new technology has been around for a while. It's a technology that goes back with Testo anyway, about 15 years. We've been making digital gauges for about 15 years now, and we've certainly gone through a couple generations of different platforms with our analog gauges, but and most of you guys hopefully may be using or have used a Testo digital gauge before. But the biggest reason for the change from analog to digital is because of that number one issue up there. It's higher accuracy reduces callbacks. It's all about the accuracy of the sensors that we're using for the pressures, all about the accuracy of the temperature pipe clamp probes that I went through with the NTC probes. There's other things that it does. Obviously, allows trending. You're charging a system while you're looking at the changes in the pressures, the temperatures, the superheat, subcooling. There's no human error because it's all done automatically for you. It does stay in calibration. I can go through that a little bit later. Another big one here, and as I see today too, the younger technicians coming into the field, it's the instrument provides excellent repeatability. That means if someone that has 30 years experience or 3 months experience in the field, if they hook the blue hose to the low side, the red hose to the high side, yellow hose to the center port, and they connect the two probes, the temperature pipe clamp probes, one to the suction line, one to the high side liquid line, the results are going to be the same, regardless of how many years of experience you have. There's no calculations. There's no method of performance or procedure method. All you really need to do is make sure that the probes and the hoses are connected correctly. The apps are a big addition over the years. All these instruments today have apps. The apps take the information from the instrument, put it into we call ours a Testo Smart app, and once you get it into your smart device, you're able to store the readings. We're able to do more calculations. We're able to send readings by email to anyone in the world, and we can keep track of our test results by developing a history of all these tests that are stored in the app itself. So, again, digital instruments have been here for a long time. I think certainly the digital gauges have been, as I indicated, introduced about 15, 16 years ago. Improvement has taken place over time. The cost of these instruments are very affordable, which I'll talk to you a little bit as I go through some of this. But how these are used are a variety of different methods, not only charging, but troubleshooting, pulling a vacuum, recovering, doing a positive pressure leak test using nitrogen, looking what we talked about, targeted superheat. We talked about enough about, these instruments calculate superheat and subcooling simultaneously. We talked a lot about evaporation and condensing temperatures. Not only are we measuring temperatures, but we're doing the calculation for you from the pressures, the low side pressure and the high side pressure. We're calculating the saturation temperatures. You'll notice on this instrument here, we're not only measuring pressures, but we're giving a reference of an analog gauge digitally, of course. This is a digital readout of an analog gauge here. And in between the gauge itself is the PSI gauge reading, the low side and the high side. Today's instruments have the capability of uploading 4 smart probes, Testo smart probes, not only the temperature probes and the relative humidity probes, but we introduced a vacuum probe, which ties into this instrument. So you no longer have a vacuum sensor that's internal in the instrument, which we found out to be inaccurate because of the leaks that created in the hoses and the connections when you do a deep vacuum. So now this is the whole vacuum side of these gauges are a separate probe that is that does the micron, that shows the micron measurement on the digital gauge. And there it is, there, close up of the gauge itself. So today's instruments, you can do a lot of different measurements. We talked a lot about superheat and subcooling and how we can do those simultaneously, but the screen can show you the vacuum side, evacuation side. So not only are we measuring in microns by using a smart probe, a wireless probe, a vacuum probe, micron probe, but we're also showing a graph of how those microns are falling and holding over a period of time. We have a pressure leak test, a very common test that everybody probably uses nitrogen to check if there's any positive pressure leaks. Putting 300 psi positive pressure on a system and then seeing if there's over time, because there's a built-in clock in the instrument, over time if there is any change in pressure. over time. Targeted superheat we talked a little bit about. We also can do a compressor test. Not only do we look at superheat and subcooling, but we can also look at the discharge line temperature on a compressor and get that simultaneously as we're reading the superheat and the subcooling. And certainly we could do a lot of different differential temperature across coils and across filters, things of that nature. But like I said, I keep saying accuracy is important. Just to give you an idea, plus or minus 1 degree Fahrenheit is the accuracy of the thermistors. And this is a thermistor, not a thermocouple. Thermocouple is much higher than that. The pressure sensors are 0.5. That's a half of a PSI. So you're going to be reading PSI in 25.4, 25.6. So you'll be reading that 1/10 of a PSI on these gauges. Same thing with the degrees Fahrenheit or the degrees Celsius. You're reading down to a 0.1, 0.2 degree Fahrenheit or Celsius. And that's all about, like I said in the beginning, it's all about less callbacks. You're looking at better tools, better accuracy. You're going to be doing a better job, a quicker job, better customer satisfaction, higher satisfaction, more recommendations, more jobs, more profit for you or your company. And what that leads to is better toys, more vacations, happy spouse. So we're looking out for you. There's other things you could do with digital gauges, of course. You can diagnose system problems. Just a chart here with looking at high pressure, low pressure, superheat, subcooling, looking at what's happening. You can determine the symptom or the problem that is occurring in the system by looking at a combination of the measurements that are coming off of the gauges. A lot of different ways, a lot of different flexibility in these gauges today. I'm getting close to the end of the presentation. I'm going to go through the rest of these slides pretty quickly, but a lot of these slides are based on Testo's product offering. You'll see the digital gauges here. You'll see the pipe clamp probes. You use 2 of these. This is the vacuum sensor. These communicate to the instrument, and the instrument communicates to the smart device. You've got distances of 300 plus feet here from the probes to the instrument. You got about 300 feet of distance from the instrument to the smart device. People always ask me, what's the price on these digital gauges? They are what I consider affordable. We got a 2-valve and we got a 4-valve case. Ours comes in hard carrying case. These are all calibrated, comes with a certificate of calibration, but a gauge, the 550S, has Bluetooth pipe clamp probes, hard carrying case. The list price is around $499. If you add the vacuum sensor to it, it jumps it up to $599. And if you add hoses, which have the low loss fittings, you're looking at $699. Here's the 4-valve. This is very common because the 4-valve manifold structure is a little bit different. It's 4-valve instead of 2. Therefore, you have a vacuum connection, 3/8 inch vacuum connection on the bottom here, and that starts at $649. And I'm just giving you suggested list prices. You contact our distributors for the correct pricing. And then the 4-valve with hoses. The 4-valve comes complete with the vacuum sensor. So again, quickly, I'm not going to go through this, but 550S is a 2-valve. We have a 2-year warranty, plus we have 1-year registration. You get an extra year if you register the unit. So you get up to 3-year warranty on these instruments. This is the 4-valve configuration. Again, 3-year warranty on registration. Again, we talked about accuracy on the micron sensor. It's a separate test. It is Bluetoothed into the 550S and the 557S. We also have a lineup of probes. These are smart probes. These are very common. These are very popular. Reason why, they're extremely accurate. You'll see a family of probes, and we're always adding to these. This is an airflow probe. This, you may recognize this as a digital manometer, differential pressure. This is a pipe clamp probe we've been talking about, air relative humidity. So we got a whole lineup of these probes now, and they come in kits or they come separately. For instance, if you don't want to use hoses at all, you just want to use an app and you don't want to go through a digital gauge, this would be considered a quick test of superheat and subcooling. You have two pressure probes, one on high side, one on low side, two pipe clamp probes, and you notice there's no display or anything. Well, that's because we're using our smart device to capture the readings. And once we capture the readings in our smart device, there's a lot of different things we can do with it. We can record the readings, we can graph the readings, we can send the readings, email. We can do a lot more calculations. So that is the end of my presentation. It took a little bit long. I appreciate the time, but I think we'll open it up to now for a few questions. And Carolyn, are you still there?
Yeah, I'm still here. Thanks, John.
Okay.
Thanks so much. And that was a really great overview. We do, like John said, we have a little bit of time left for some questions. So if anyone wants to ask anything, please go ahead and submit it in the chat panel on GoToWebinar, and we'll try to get to as many as we can. I do have a few here, so we can go ahead and get started. The first one is, what's the difference between the new Testo app and the existing Testo refrigeration and smart probes app?
Okay, that's a good question. Testo, when we introduced the new digital gauges, the 550S and the 557S, we also introduced a new app, and it's called the Testo Smart App. All our apps are free, regardless of what instrument you're using. But the Testo Smart App is an app that is can be used both with our digital gauges as well with our family of smart probes that I've shown in the previous slides. So instead of using two apps, one for digital gauges, one for smart probes, we combined it into one app called Testo Smart App. And we've also made some feature changes to it as well. We provide more graphics. It's easier to use. The biggest thing too that we added is you can store customer information, detailed information, address, company name, email, phone number, contact person, contact information. We can also store what we call, under the customer or the company name, we can store the application. Say you got 3 air conditioning systems that you got to test. Well, you can identify all 3 of those systems by equipment type, by location of the equipment, under that customer name. And you have a lot of memory storage where you can store thousands of tests, superheat subcooling test under the customer name and that application within that customer name. We got memory storage. You can store all the tests, and then we do a few more calculations. Not only do we do the refrigeration, air conditioning calculations, but we do volume flow measurements. So we can calculate cubic feet per minute when you're using an airflow instrument. We can calculate cooling and heating capacity, where you're checking airflow and you're checking your supply and returns to check for the capacity of the equipment, see if we're meeting the capacity of equipment, and some other tests that we're doing. So there's been a lot of enhancements on this new Testo app. It's Testo Smart, and it's free regardless of if you use Testo or if you don't use Testo. You only can use it on the Testo instruments, unfortunately.
Okay, great. Another one is, what are the calibration requirements for your digital gauges?
Yes, as I indicated through the presentation, we're using very accurate sensors. We have 2 pressure sensors that are located on the low side and the high side of the instrument internally. And those pressure sensors, when you turn the instrument on, if you're not reading 0 PSIG, let's say you're reading 0.1, 0.5, there's a button on the instrument that you press, and it zeroes out the pressure sensors to the atmospheric pressure. So that's all you need to do. There is no real calibration unless you damage the sensors or there's a restriction in the block itself where you may need to send it back to Testo. This doesn't occur too frequently, but if you got a restriction or something damages that pressure sensor, which takes a lot, by the way, um, you may have to send it back for calibration. As far as the temperature sensors, as I indicated, NTC probes do not need to be calibrated. Only the thermocouple probes need to be calibrated periodically, and we don't use thermocouples with our digital gauges.
Okay, perfect. And it is 3 o'clock, so I think we're running out of time today. So any additional questions? I see a few more here. John will go ahead and respond to those via email. I do want to mention that this is a NATE seminar, and as such, attendees receive 1.5 CEUs for attending. So to get your credits, please contact John using the contact information shown here. And I will also provide instructions for this for all attendees in the follow-up email. So look out for the email with the recording, and there will be instructions on how to get your credits there as well. Okay, and on behalf of Testo, thank you to everyone that attended our session today. And thanks very much to John as well for a really great session on understanding superheat, subcooling, and saturation.
Thanks, everybody.
Have a great day.